10. Strain energy. It is form of energy which is stored in material when an external load is applied on it. It is scalar quantity with unit Newton meter or joules. Resilience. It is strain energy stored in material within proportionality limit. P load applied, delta is deformation, L is actual length, A is area. P delta, it will be a straight line. Inside proportionality limit, this any point without within proportionality limit, that area is called resilience. U is equal to half P into delta, which is area Newton meter units. So within proportionality limit, delta is equal to PL by AE, U is equal to P square L by 2 AE Newton meter. Sigma is equal to P by S, P is equal to sigma A, epsilon is equal to delta by L, delta is equal to epsilon L. Put P comma delta in equation 1, U is equal to half sigma A into epsilon L is equal to half sigma into epsilon into A into L. Strain energy per unit volume is equal to half into sigma into epsilon, Newton meter per meter cube. Area under sigma epsilon will give strain energy per unit volume. By Hooke's law, sigma is equal to E epsilon, epsilon is equal to sigma by E. U by strain energy per unit volume is equal to sigma square by 2E, Newton meter per meter cube. Strain energy due to basic loadings. First, axial loading, P, U is equal to integral Px square dx by 2AE. These limits will be in terms of length for x. If shield load VVx U is equal to integral Vx square dx by 2Ag. Bending U is equal to integral of mx square dx by 2EI. For twisting U is equal to integral Tx square dx by 2Gj is equal to T square L by 2Gj if T is equal to constant. U is equal to half T theta. Find out strain energy stored in bar due to self weight. Px is gamma ax. So integral of gamma ax whole square dx by 2ae is equal to gamma square a square by 2ae into x cube by 3 from 0 to L is equal to gamma square a L cube by 6e. Strain energy due to torsion. Torsion T applied. The strain energy stored in elemental area du is equal to half tau into pi into 2 pi r L dl. dA is equal to 2 pi r. Along the length 2 pi r L dr is volume. Pi is equal to tau by g. D is equal to tau square by g into pi r L d dr. Tau by r is equal to tau max by r. Integral 0 to u du is equal to integral 0 to capital tau max square by g capital square into r square pi r L dr. U is equal to tau max pi L by g r square into integral 0 to r small r cube dr. Tau is equal to tau max square by g r square into pi L into r power 4 by 4. U is equal to tau max square by 4g into pi r square L. U per unit volume is equal to tau max square by 4g, Newton meter per meter cube. Proof resilience UP. It is strain energy stored up to proportionality limit and it is maximum value of resilience up to proportionality limit. Proof resilience like UP till this whole area up to proportionality limit P area in P delta. Modulus of resilience UP per unit volume. Proof resilience per unit volume sigma epsilon. Modulus of resilience is a property of material like modulus of elasticity and modulus of rigidity. is fixed is equal to sigma PL square by 2E. Proportionality limit sigma is fixed, E is also fixed. So this is material property, modulus of resilience. Toughness P delta up to fracture point. It is maximum amount of strain energy that a machine can store just before the fracture. Modulus of toughness. Modulus of toughness Like for high carbon steel it is brittle, it will be like this. For mild steel it will be diagram of sigma epsilon will be like this. Ductile material are tougher than brittle material. We can directly see from area is more for mild steel which is ductile, low for the high carbon steel which is brittle. If a material is subjected to impact loading, then it should have good amount of toughness. If a material is subjected to impact loading, because it should absorb more energy. Note in sigma epsilon, x increases, ductility increases, y increases, strength increases, area increases, toughness increases. X increases means it will be like this, mild steel, ductility increases. Y increases means sigma y is more, which means strength increases. Area increases means toughness increases. Loading and unloading of material. Loading within elastic limit. If within elastic limit, if you load and unload it, it will follow the same path. Loading beyond elastic limit, if you load beyond elastic limit and leave it, then they are not come, it won't recover completely. Only few particular part will be recovered. For example, this will follow the line like this, o dash. This is plastic strain energy, this is elastic strain energy as it is recovered. O dash is permanent set, because that permanent deformation will be there. Hey, and the slope of this is nothing but a Young's modulus. In a question, everything is given from A point, it is unloaded. Then here till epsilon b will be there. Here 0.5 comma 500 is given epsilon. Then we have to find epsilon b is equal to question mark. And the slope of this line BA is nothing but BA is nothing but E, which is 200 into 200 gigapascal. 500 minus 100. Here sigma b is given as 100 by 0.5 minus epsilon b is equal to 100. And another questions are similar model. The normal strain energy calculations we have done it. Resilience, toughness also, area we can get it. Hmm. Okay, one question. U1 is equal to P1 P1 square L by 2AE, Pu2 is equal to P2 square L by 2AE. But if they are combined, two loads are applied, then P1 plus P2 whole square L by 2AE. That means U greater than U1 plus U2. You cannot apply you cannot add strain energies directly if two different loads are there. You have to put inside whole square and then integrate or add. Okay. Strain energy T square L by 2GJ. Another question. Impact load. If a weight W is dropped from height H, then delta H is we have delta H deformation will be there, and total length L. V square is equal to U square plus 2GH, U square 0 as dropping. H is equal to V square by 2G. Sigma ST is equal to WL by A. Delta static is equal to WL by AE. That means if load is applied gradually, but here it has dropped. Potential energy of weight W is equal to strain energy in the column, because only potential energy is decreased and strain energy is gained by this rod. W into H plus delta H is equal to sigma impact square by 2E into AL. W into H plus sigma impact L by E. Delta H is sigma impact into L by E is equal to sigma impact square by 2E into AL by 2E into AL. Sigma impact is equal to W by A into 1 this sigma impact square. This is quadratic equation. By solving this quadratic equation, we will get sigma impact is equal to W by A into 1 plus root of 1 plus 2H by WL by A. This is impact factor. Sigma impact is equal to sigma static into impact factor. Delta impact is equal to delta static into impact factor. Impact factor is equal to 1 plus root of 1 plus 2H by delta static. Just above steps, if you write find h is equal to v square by 2g, delta stat, find delta static, then impact factor, delta impact, sigma static, sigma impact. Impact from impact factor we can get everything, 1 plus root of 1 plus 2h by delta static. Weight is dropped here, then find maximum deflection. Gradually applied load 0, 1 or 2, so on W. Gradually applied load W. Suddenly applied 0 to W. Impact H is equal to 0. Impact factor is equal to 2. H is equal to 0. Then impact factor is equal to 2. Suddenly placed on weighing machine. Sigma sudden is equal to 2 into sigma static. Sigma sudden is equal to 2 into sigma delta static. Here delta static is W into okay, we have to find all these. Okay, this is on workbook question. Okay, done.